Hi everyone, in today's lesson we're going to talk about continuity over an interval. First, what we need to do is discuss the domains of specific functions. Now I have 6 main functions here that you should be familiar with. We have linear functions, quadratic, cubic, functions of higher degree. These are like polynomial functions. This one is x to the 4th or something of that nature, odd root functions, and absolute value functions. What you should notice about all 6 of these functions is that they all have infinite domains. What that means is that they go from negative infinity to positive infinity, negative infinity to positive infinity. Every single one of them have a domain that stretches left and right from negative infinity to positive infinity. Now, what about functions that don't have infinite domains? These are the 3 main functions that we say don't have infinite domains. We have rational functions. The reason why they don't have infinite domains is because there's an asymptote. If you want to draw it in, feel free. There's an asymptote down here at x equals 0. So the domain is really from negative infinity to 0, and then from 0 to positive infinity. Even root functions such as the square root of x also don't have infinite domains. What's great about the square root of x is that we should understand that we can't take the square root of negative numbers. If we did, we'd have imaginary. So that tells us the square root function needs to be greater than or equal to 0. And then log functions have asymptotes just like rational functions. The most basic log function has an asymptote at x equals 0. So this tells me that the domain of the log function is from 0 on. In this case, we can't equal 0, right? We can't equal it because that's where the asymptote is. So just to recap, the domain, this is the symbol for all real numbers except x equals 0. So in general terms, it's all reals except for the undefined values. Even root functions, the domain is anything greater than or equal to 0, and the root must be 0 or positive. And for our log functions, we need to have a domain that is greater than 0. So let's practice some of these. So I want to state the domain of each function. So let's take a look at the first one. So the first one is a rational function. Why rational? Because it's a fraction. And we know the domain of rational functions are all real numbers. So this is the symbol for all reals. So all real numbers except for where it's undefined. So we have to find where it's undefined. So if you remember, undefined is when we set the denominator equal to 0 and solve. So what this tells us is that if I were to plug in -5 into the denominator here, that would give us 0. -5 plus 5, that would be undefined. So technically this is our vertical asymptote because nothing canceled, so there's no holes. So we can say the domain would be all real numbers except for -5. Okay. Second example, we have a square root function. We know it's a square root because we see that square root. And the way that we solve for these domains is we have to make sure that the stuff inside the radical, so all of this, the x minus 2, has to be greater than or equal to 0. Right? It can't be negative because that's when we have imaginary numbers. So we just do a quick solve, and then we're going to say that x is greater than or equal to 2. So that's my domain. We can write the domain in 2 ways. We could say from 2 to infinity, or we could just write x is greater than or equal to 2. Either way is appropriate to write the domain. Okay, next we have a log function. This is a log function because it's an ln, right? ln is log base e. So with ln, we know that the inside of the ln has to be greater than 0. It can't equal 0, it has to be greater than 0. So we're going to set the inside, 2x plus 4, to be greater than 0. We're going to do a quick solve. So we'll minus 4 on both sides and divide by 2. So we have x is greater than -2. So again, there's 2 ways we could write this. So we could say from -2 to infinity, or we could just write that x is greater than -2. Either one is an appropriate way to write the domain. Okay, So let's just talk about how we could use this stuff to answer test-like questions. So here's example number 1. It says, let f be the function given below. On which of the following intervals is f continuous? Well, since we have a piecewise function, it would be in our best interest to check where the functions change. So here we're going from exponential to rational. We want to see if it's continuous there at x equals -1. Then we're going from rational to quadratic. We want to see if it's continuous there, and then so on and so on. So we have to just take a look at those connecting points, which are shown here, 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 and here, right? So let's look at the first one. We know that it goes from exponential to rational at x equals -1. So we're going to check to see what happens at x equals -1. So we're going to plug into our exponential. So 3 to the -1 we know is 1/3, or 1/3. And then we're going to plug into our rational. So 2 times -1 plus 3 over -1 plus 4. So this is actually 1/3 as well. So that works out nicely. So that means it's going to be continuous from here to here, to this jump. Okay, now let's try at x equals 0, which is this connecting point. So let's try that, x equals 0, and we'll try into our rational function and then into our quadratic. So let's try 0. So 2 times 0 plus 3 and 0 plus 4. So this gives us 3/4. And then we're going to plug into the quadratic. So 0 squared plus 2 times 0. And that gives us 0. So look what's happening here. Since these are the same, it's telling me that I'm continuous from here to here. But since when I plug in 0, 3/4 and 0 is not equal, that tells me that there's going to be a jump at that point. So we know it's not continuous at x equals 0. So at x equals 0, we have a jump, which makes this not continuous. So let's try to find the interval here that has 0 in it, and we know that that's where it's not continuous. So -5 to 0 doesn't include 0, so that's okay. -0.5 to 3. Well, 0's in between that, so this one's out because there's a jump at 0, and 0 is in the middle of that interval. 3 to 5 doesn't include 0, and 5 to infinity. So, okay, we've made some progress. So now let's take a look at 4, right, because that's the next joining point. So we're going to join the quadratic, x equals 4, with the tangent, the trig function. So 4 squared plus 2 times 4. That would give us 16 plus 8, which is 24. And then let's try tangent. So tangent of 4. Now, without a calculator, you really should know that tangent of 4 is not going to be 24. It's going to be some irrational number. So we know that number is never going to be equal to like an even 24. So we can say that there's also a jump at x equals 4, because whatever tangent of 4 is, it's not going to be 24. So here we also have a jump. So that tells me that anywhere I have an interval of 4 or a value of 4, it's going to be a jump or discontinuous. So here from 3 to 5, 4 is in that. So it can't be that. Why? Because there's a jump at 4. And let's look at D. So from 5 to infinity, that one's actually tricky. We have to understand that from 5 to infinity, we're talking about a tangent curve. So if you remember, tangent will always have asymptotes. So this one is going to be not continuous because tangent is not continuous. So not continuous because tangent is not continuous. And if you want to just recall, the tangent curve, if you remember, kind of looks like a whole bunch of x to the thirds with asymptotes, right? That's our tangent curve. So we know that no matter what, that if we go to infinity, we're going to keep repeating these and we're always going to have those asymptotes. So that really leads me to my last and final answer, which should be choice A. So let's see if that makes sense. So from -5, which is all the way here, to about 0. So 0 is here. So between these two, we knew it was continuous because they were the same. So from -5 all the way to 0, we know it's continuous. So that is our answer, and that's why. Now, I know example number 2 is not exactly the same, but I kind of want to see if you can do this one. Just try it on your own and try to prove it. It's just asking you which of the following functions are continuous. So I want you to explain your answer. Like, try to see if you can come up with a reason why the answer that you're choosing is correct. And we will start class by going over that one tomorrow. All right, have a good night.